Hello everyone and welcome to another tutorial on Flutter. In today's session, we will build a tic-tac-toe game using the Flutter's Casual Game Toolkit. To begin with, we will create a multiplayer mode where two players can compete with each other. We'll then develop a single player mode where the players can compete against AI of different difficulties. The level of the game will determine the difficulty of the game. The initial levels will be easier with AI choosing random moves. The intermediate levels will become slightly competitive when AI attempts to make moves logically. In the final levels, AI will be smart enough to always win or at least draw the game, which we will achieve by using the Minimax algorithm with alpha-beta pruning. We'll also introduce M by N tic-tac-toe to add variations to the game. Finally, we will try to simulate the gameplay between AI where they will play against each other. Let's jump in and begin this tutorial. Clone the starting repo from the link in the description section below, which I have downloaded from the Flutter's official game template repository. Open the project in any of your preferred IDE. I will be using Android Studio as usual. This repository consists of a minimal starter game that already has some code ready for us. It uses some libraries such as provider, shared preferences, audio players, etc., which are being used for various purposes such as managing state, persisting data, playing sounds, etc. Additionally, it has some screens configured for us using GoRouter package such as the main screen, the level selection screen, the gameplay session screen, the winning screen, and settings screen. Apart from these, we can integrate add mobs, game services, in-app purchases, crash lytics, etc. in the game with minimal changes. I will not go on to explain the structure of this code now. We'll explore them as we progress along this tutorial. Open the main menu screen and make some changes there. Update the text to tic-tac-toe and then add a button that will take the user to the multiplayer mode. Update the URLs for each game mode. Also update the route configuration so that it supports the URL we just added. Restrict it to support only these two URLs. For anything except those, redirect the routes to the single mode of play. Add another route for the play URL and redirect to the single play mode as well. Add a parameter in the level selection screen to distinguish between the game modes. Using that, display the text accordingly. We also have to update the route to the play session screen since we updated the parent route earlier. In the play session screen, we will develop a game that can be played between two players or between a player and an AI. Let's remove all the widgets that we won't need in our implementation. Create a widget where we'll build the game UI. The UI is divided into 3 sections. Create 3 different widgets for each of these sections. In the upper half of the UI, there will be action buttons. In the middle, there will be tic-tac-toe board, and at the bottom, there will be a restart button. Place these widgets in the UI. Wrap the main section widget with the center widget, then by expanded widget. There seems to be some error in the main file. We cannot use the const modifier here since the level selection screen no longer passes constant parameters. For a 3x3 game board, there should be 9 boxes where the player fills in with X's or O's alternatively as the game progresses. Let's use our grid builder widget to represent these tiles. Using a delegate, we can assign cross and main axis spacing. The cross-axis count should be 3 and the children count 9 for a 3x3 tic-tac-toe. In the item builder property, pass a container for now with a text view inside displaying its corresponding index position. We now have this 3x3 representation of the game of tic-tac-toe with each tile represented by a distinct number. Instead of this number, let's represent them on an XY plane so that it will be convenient for us while writing logic. Now each of these tiles can be identified uniquely by XY plane representation. Update some of the properties of grid view like shrink wrap, physics, and padding to make it go along with our design and some calculations that we'll do a bit later. Let's generalize this 3x3 tic-tac-toe board to an m by n form where m and n are greater than 2. Now with this configuration, we can generate tic-tac-toe board of any size. Run this in an simulator. Create a model class tile in the Game Eternals folder. This class represents a square tile of a tic-tac-toe board and has two attributes, one for each coordinate axis. Create another class that will contain the design for each individual tile. Inside of this, add an inkwell widget and then move the content from the main board session to here. Make the necessary changes to use this widget in the main board session widget. Next, let's remove the background of each tile by removing this container widget. We'll draw the separating lines using custom painter class. With this class, we can draw different kinds of lines, shapes, etc. Think of this as an two-direction coordinate axis where the origin lies at the top left. The height and width of the plane are derived from the parent. Create a new file, board lines. In this class, we will use the custom painter widget to draw the lines that we need in the tic-tac-toe board. Create another class, games lines painter, and extend custom painter. We need to implement two methods here. In the paint function, we'll draw the lines in the canvas that it gets from the parameter. With the draw line function, we can draw a straight line on the canvas by passing starting and ending points, as well as paint object. Create a paint object with a color that we have in the parameter. We need to draw m-1 horizontal lines and n-1 vertical lines. Each line lies at the end of each tile. Let's do some maths and draw these lines. Repeat similar approach for the vertical lines as well. Let's use a stroke width of 8 and also introduce some padding. In the should_repent function, we have to pass the condition when the repent might be needed. That is the case when the attributes changes. We can check this by comparing these attributes with the old delegate. We can use this painter by using a custom paint widget. Wrap this further with the repent boundary widget so that the paint animation does not go out of bound. Pass the color to it from the palette. Now in the main board section widget, we just have to put it together using the stack widget and set expand stack fit. Also, wrap this whole content with the aspect ratio widget to keep the lines within the boundaries of tiles. Make a copy of this whole implementation and rename it to winning lines. As the name suggests, we'll use this for drawing the winning lines. Apart from these two attributes that we already have here, we'll be needing two more for the starting and ending tiles. The idea is to draw the winning line from these by finding out starting and ending point. Finding the points are a bit tricky as we have to choose the starting or ending point of the tile as per the condition for the horizontal, vertical, or diagonal lines. We also have to update the values in the should_repent function. Use red ink here to draw the winning line and also pass the necessary attributes. We can now use this widget to draw the winning line as soon as someone wins the game. For now, let's comment these out. We now have this UI where the users can click these square tiles from where the event is triggered with the tile that was clicked as its parameter. Instead of the text that is displayed here, we'll make them empty and fill them up alternatively with X's and O's as the players click them. Before proceeding to do that, let's first create some model and state classes. Add an enum to represent the options that are the letters X and O. Include another option, none, to represent empty. Next, add a board setting model class to store board configurations like size, the number of tiles needed to win, and the option the first player is using. In addition, add a boolean to indicate who will start the game. Also, add a getter to evaluate the option that the opponent is using. Use a boolean variable player is X to indicate the option that player 1 is using. Add a constant named constructor that returns default board configuration with a 3x3 tic-tac-toe. Finally, create the board state class and extend it with change notifier. This is our main state class and most of the game logic will revolve around this. Inside this, create a map variable for storing every move as a key value pair of the tile and side option. Then we can know if the current tile is taken or not by searching its value in the map. We can also get the value at each tile from the map variable. Create a function to occupy the tile. We can occupy the tile by assigning the current side or turn to the clicked tile in the map. Since it's a turn-based game, the current turn could be calculated by knowing the total number of moves that have been made are even or odd. But the side picked by the players is stored in the board setting class. Add a variable to store the board settings and make it final. Create a private constructor with the setting variable and a new function to instantiate this class. Now we can assign the values properly in the current turn function. This would be correct if player 1 always starts. Update the function using the opponent starts variable from the settings class. Update the moves with the clicked tile and the current turn combination. After assigning the values, we also have to check if the game ends. That is, there is a winner or a draw. Add a boolean is locked variable to lock the board temporarily when the calculation is still going on. The larger boards with the higher values of M and N may need some time for the calculation, and during that interval, we might want to lock the board to avoid errors. Add array variables to store the winning lines and combinations. Add some getters to check if the game has started and if the opponent is a human or an AI. Assign it false for now. We will update it later when we will add AI opponents. Also add a value notifier that we can trigger if the game ends with a win or a draw. Create a initialize function to initialize the board and a clear function to clear the board. Get disposed of the result notifier in the dispose function. Add a function to check if the players can occupy the clicked tile, which is when there is no entry of that tile in the moves variable, or the enum type none is stored in them. Before proceeding further, let's discuss briefly about the change notifiers. A change notifier is a simple class where we can store different variables that can notify the widgets that are currently using the variable in case of the variable update so that they can be updated with the latest data. They can be created in the init state function and pass on to the widgets. Another more popular and better approach is using it along with the change notifier provider widget from the provider package, which does not require the stateful widget and also gets destroyed as soon as removed from the widget tree. We can use them by using the consumer widget or by using the context.select, context.read and context.watch methods. We can call the function notify listeners to notify all the listeners. Value notifier is a special type of change notifier that stores only a single value. There is also a non-mutable alternative state notifier. I will cover these topics in more detail in a separate video. Consider the following code with a value notifier. Initially, it has an empty value which is listened to by the test widget. Now, whenever the value changes, it notifies the test widget, which in turn updates its value. Also, it should be noted that the test widget is not notified when the value is updated to the same value. That is, if initially it has 1 as its content and it is updated to 1, then no notification is sent out. But if the value is changed to some other value, then the notification will be sent. Hence, it also reduces unnecessary renderings. Consider another example with the object board setting. In this setup, the notification is sent out even if there is no change in them. If we compare two objects of board setting, then it will print that they are not equal to each other because they will point to a different memory location. Hence, the value notifier also detects change every time even though there is no change. The solution to this will be to specify the attributes that would be used during the comparison. One solution is to override the equals to operator and specify the attributes here. We also need to override the hash function for this to work properly. Another solution is by extending the equatable class from the equatable package, but we'll not look into that in this tutorial. Now this setup will only notify if there is change in the values in the object that we have specified. Let's also perform operator overloading in the tile model class. In the game session screen, replace the game level state variable with the instance of the board state. For now, pass the board setting of 3x3 and also add the listener for the game result. We will not implement the game services to post the scores as it is done here. We will just show the celebration confetti using the implementation that we already have here and then show the result to the players using the winning screen. We'll come back to this after we have completed writing the winning logic. We do not need the size parameter here because we'll be using the values from the state variable. Replace all of the values from the state. Next, we'll implement the clicks in each tile of the board. Check if it's not locked or occupied, and if so, occupy the tile. Also, display the value in each tile from the board state and increase the font size as well. We can now occupy the tiles alternatively with X's and O's. To check if someone has won, we have to look for the K matches on the board either vertically, horizontally, or diagonally in both directions. Instead of looping through all the combinations to check for the win, what we can do is to start from the tile that the player had selected and then check for the matches in all the possible directions from there. If it matches up to the count needed to win the game, then we have a win. The function for checking the win will need the tile that was clicked and the current side option, which will contain either X or O. To look for the winning combination in the vertical direction, iterate up to k-1 and in each iteration match the tiles both upwards and downwards. If there is a match, increase the winning count by 1 for either of the cases. Finally, if the winning count matches up to the needed count, we have the winning combination in the vertical direction. We are looping to k-1 only because we already have one match, which is currently occupied tile, where k is the number of matches needed for a win. We can return true here, but there may be the cases of two winning combinations. So we'll continue the loop for all the directions. Store the result in a variable and break the loop. Initialize these variables and then return the result from the function. We will also store the winning tile combinations and the start and end tiles of the winning combination to display winning combinations and winning lines on the game board respectively. Now reset all these temporary variables and then copy the above code to check the winning combinations in horizontal direction. Here, check the tiles in the left and right direction. Repeat the process to match the combinations diagonally that run from top left to bottom right. Finally, check winning combinations diagonally that run from the bottom left to top right. This code can be optimized to reduce the execution time. We'll not look into that in this tutorial. You can challenge yourself to find a better solution than this. In the main board section, we can utilize the winning lines variable from the board state to draw the lines to show the winning combinations. In board tile widget, we can utilize the win combos variable from the state to highlight the tiles. Make the text bold and highlight it with red ink from the palette. Use the animated scale widget to animate the text by scaling it a bit. Specify the duration for the animation to 300 milliseconds. Let's increase the size of the board a bit so that we can have wider test cases. In the board state, execute the function to check if someone has won the game. Also, lock and unlock the board before and after executing the winning function. Here the setting is a 4x4 board, with 3 being the number of combinations needed for a win. I think the winning logic is working correctly. We'll correct it later if there is any issues with it. We also have to check for a draw before continuing to the next turn. The game is drawn if all the moves are taken, but we first have to check if there is a win. Store the winning side option to the game result and then notify its listeners. We can know a draw by checking if there is no win, even though all the moves have been made. Store the none option if there is a draw. The game will either end in someone winning the game or a draw. After that, we'll display the result page. For the result page, let's utilize the page that we already have in this template. Read the board settings and message from the extra parameters that will be needed for replaying the game and showing the result message respectively. On the Win Game screen widget, add the parameters that we configured in the routes and update the UI to display the result message and a button to replay the game. The button will allow the players to replay the game in the same game configuration. If the game is won, then the game is halted and the winning confetti is displayed. We also have to handle the case for a draw. Add some delay to allow users to see the board for some time before the winning lines are displayed. When there is a draw, winning confetti should not be displayed. We'll only show the result screen with some suitable message. Add a function to check if the first player is the winner by taking the winning side as the parameter. Use the function to check the winner and display the message accordingly. Currently, we can only set one name from the setting. Let's show that name for player 1. We can update the settings screen to allow inputting the name of the second player as well. There is some issue when the game is drawn. We should compare the value property of game result rather than game result itself. The game is now working properly for the versus mode, where 2 players plays the game, each trying to get a win. This UI lacks some controls that may be very handy to the players. For example, a button to restart the game midway, go back to the level selection screen, etc. Add a button to go back. Add the text in the middle to display the current game mode and another button to take the user to the settings screen. At the bottom of the UI, we'll add a button from which we can restart the game midway. We'll display that button only after the game is started, that is, at least one move has been made. To complete this mode, let's modify the level selection screen to allow the users to select different types of board configurations. Create a model class GameMap in the level selection package. This model class has ID and board setting as its attributes. Add an attribute GameID in the board setting model class to associate the map ID there. I have created 4 maps here with different configurations. We can add more later as per the game requirement. I have added a file map selection card in the level selection package. It has the design of the card showcasing the board of different sizes, winning configurations, and clicking it will allow the players to play in it. Also, let's modify the route configuration of the gameplay session such that it reads the value from the URL and derives the configuration based on that. Return a default 3x3 configuration if no configuration is found for that value. For AI mode, return the default configuration as well. We'll come back to it and modify it later. In the level selection screen, use a grid view widget to display the list of maps that we had defined in the game map file using the map selection card widget. The first version of our game is ready with versus mode. The players can now select from the listed board configurations and compete with each other. Next, we will proceed to develop another game mode where the users can play with AI. Create an abstract class AI opponent to represent different types of opponents that we will be creating. We need the AI to decide the next move. Create a function for that. The first opponent that we'll build is a simple one and it will be very easy to beat. That chooses its next move randomly from the available moves. Let's first complete the AI mode with this random move choosing opponent. Later we'll add more opponents to make the game more competitive. In the game setting model class, add AI opponent entry and make necessary changes. In the board state class, modify isAIPlayingGetter to get its value by checking the AI opponent. In the occupy tile function, an AI move should be made. The AI will make the move as soon as the player had made their move if there is no win or draw. Call this function to make the move for AI as well. Add a boolean parameter to let the function know who is making the move and use it to make the move for AI. Also, we have to address the case when AI performs the first move. We can of course use the choose next move to decide it, but we'll force the UI to choose the center tile as its first move. In levels.dart file, add an entry board setting to the game level model class and then update the level list with some game configuration with the random opponent. Create the level selection card with these contents in the level selection package. It contains a simple card design with a level ID that will redirect the game to that specified level. Implement this design and levels in the level selection screen. For the mode that is not a versus, use a grid view to display the list of levels using the level selection card design. In the main file, update the route configuration for the AI mode. Obtain the level ID from the URL, load the level definition, and pass it to the widget. Additionally, we have to handle cases where a level definition is not found. I am leaving these parts as a to-do for later. In the play session screen widget, update the routes to the result screen as per the game mode. Update the message also to specify the winner correctly. In the win game screen widget, update the route to replay the game. Finally, in random opponent class, implement the function to decide the next move for AI. Loop through each of the tiles and store the tiles that are yet to be taken by the players. From the available options, use the random functions to choose the random move. Here the AI is making its move, but the move it's making is not smart enough to beat the players. Create another class, Thinking Opponent. Unlike the previous opponent, this opponent will not choose its move randomly. It inspects the board carefully and checks if the game can be won. If not, it checks if the player can win in their next move to restrict them from winning. It seems the function to check the winner is declared as private. Make the function public so that it could be used from outside the class also. We need to update the function to check if someone has won, since it will also affect the state variables. Add an optional variable, checkOnly. We can directly return true from here because it is not necessary to check in all the directions for this case. If it satisfies the condition in one direction, then we can assume the win for that particular move. Check if the game can be won. Next, check the win for the player so that AI can block that particular move. If it finds the move that can win the game for itself or the player, it chooses that particular move. If it cannot find the moves that satisfy any of the two conditions, then it will choose the random tiles from the available ones. To test our new opponent, let's add some more levels to the level list. Make the 4th level 3x3 with the Thinking Opponent. 5th level is the same as the 4th level, but the AI starts the game here. 6th level is the 4x4 game with the Thinking Opponent, and AI starts the game in this as well. The AI is making better choices than the one we played before. Its goal is to win and also deny opponents the win. If that is so, can we beat this AI? The answer is yes. To understand this, let's take the example of a 3x3 board. If two players are aware of all the moves, then no one can win. The game will always end up in a draw. There can be many scenarios when the game can be won through two alternatives, so that the win is guaranteed. The expert players will know about these and try to bring that scenario in their favor to win the game. For example, if the first player starts in the middle and the second player places their move on any tile other than the 4 corners, then the second player is guaranteed a loss, provided the first player makes their move properly henceforth. Alternatively, if the second player places their move on the corner, then the game will end up in a draw, provided both of them chooses their best activity going forward. The current AI cannot avoid this situation as it makes a random move if it cannot find the moves it is looking. For example, in this scenario, the AI can choose any random move since it won't find the move that can win for it or the player. And if it selects the middle tiles, then the players can win the game. Next, we'll build the smart AI opponent using the Minimax algorithm. It's a backtracking algorithm that uses the recursive approach to find the optimal move, which can be used in a turn-based game like tic-tac-toe, chess, etc. By using this algorithm, AI will play every possible move from the given match state and choose the optimal move. By following this approach, AI can always win if that is possible, of course. Let's consider the given game state where X is trying to choose the optimal move. We can clearly tell if X chooses the tile at the bottom center, it wins. But X needs to decide that programmatically using the Minimax algorithm. There are 3 possible tiles that X can choose. If X chooses a top center tile, then O has the option to go to the bottom center or right center, after which X has one place remaining, which is bottom center or right center as per the move that O made prior to it. By choosing that first option, X can either win or draw. Similarly, the second option yields a draw or a loss, which is definitely the worst option than before. The last option guarantees a win to X, hence it's the best option among the three. In the Minimax algorithm, there are two participants. One is termed as maximizer and tries to choose the maximum value. Another is the minimizer, which tries to choose the minimum value. They play alternatively, each trying to choose the optimal move, resulting in a win for their own. Let's consider the following tree that has some values at the leaf nodes, and it's the turn of maximizing player to choose between the three moves. From the leaf node, we can backtrack the values of the intermediate node. In this row, it's the turn of maximizing player. It chooses the maximum value between 3 and -1. It will pick 3. Similarly, each node in the row does the same to choose the maximum value. We can now compute the values at the minimizer. Unlike maximizing player, it chooses the minimum value. With all these values, the optimal path would be along 3. I have chosen a very simple tree for demonstration purpose. In the real life, the tree can be much more complex than this. In TicTacToe, we will have only 3 values. One player can be max, representing +1 for their win. Another can be min, representing -1 for their win. And 0 will represent draw. Let's represent the previous game state in the Minimax tree and try to choose the optimal move. Suppose X is the maximizing player, that means O is the minimizing player. The win for X will be represented by 1, while the win for O will be represented by -1. All the draws will be represented by zeros. As we did earlier, we can calculate the intermediate values. The minimum player chooses the lower value among the two, while the maximum player chooses the higher value. By inspecting all the values, the optimal choice for X to make is the right path through which it is guaranteed to win the game. Now, using this algorithm, we'll build another opponent, make a copy of one of the previous opponents, and call it a smart opponent. In options, we have the list of available moves from which the AI has to choose the optimal move. We iterate through each of the moves, compute the score for each of the moves, and choose the one with the best value. Make the move for the AI, calculate the score for that particular move using the Minimax function, and then undo the move because the AI is only checking, not actually playing that move. Let's suppose that AI is the maximizing player, so the best score for it will be the higher values. Store both the best score and the best move. The initial value for it should be the minimum value possible so that the first condition is always satisfied. The minimum value is -1 for this game, so its value can be -1 or less. I will use -infinity here, which is the lowest value possible. The AI makes the move, compute the score for that move, and then undo the move again. If the score exceeds the current best score, we update the best score and the best move. The Minimax function will require the board state, current move, a boolean value to indicate the player is maximizing or minimizing, and the remaining list of moves. We can also have a parameter representing the depth of the tree, but we'll be not using that in this game. Pass the respective values to the Minimax function above. Is maximizing will be false since it's done maximizing and it's passing the control to the minimizing player. Options will be options excluding the value it just used. The Minimax function is the recursive function that runs until one of the players wins or they drew the game. That will be the terminating condition for this recursive function. Return -1 or 1 depending on whether we are maximizing or minimizing. We do not have to check both the condition for win and loss since the function has someone won will do the work for us for both cases. Return 0 if the game is drawn. The current turn will have the wrong value here since we've already played the turn above. Move this section down below to fix the error. In the minimizing case, the initial value for the best score will be positive infinite. We have to compute the best score from every available move, make the move, calculate the score for that move, and then undo the move as we did above. The best score here will be the lower values among all the computed values. We don't have to play the move as it's already done in the Minimax function, but we have to undo the move. Finally, return the best score. Repeat this for the maximizing case as well. The Minimax function will be called recursively until all the values will be calculated at the leaf node, which will be either 1, -1 or 0, representing a win for X, win for O, and draw, given that X is the maximizing player. In this example, AI plays its move as a maximizing player while the player plays their move as a minimizing player. We can also do this in reverse, that is by making the AI minimizer and the player maximizer. In levels.dart file, let's add some more levels with the newly created opponent. We'll add only 3x3 configurations since a 4x4 board will take a bit longer time. We have some issue here. This can be resolved by declaring the return type of the Minimax function as double. The AI is playing very well here. It's impossible to win against it. We can either lose or, in the best case, through the game. The first move that the AI made is taking a comparatively longer time. We can see that from UI being a bit laggy there when clicking the tile to make the move. We can also verify this by computing the time to get that move. The time taken is definitely greater computing the next move. We can improve this a bit by using alpha-beta pruning. I will not go deep into explaining it. It needs two extra parameters, alpha and beta. Alpha will store the maximum value that the maximizer can contain, while beta will store the minimum value that the minimizer can contain. And when beta becomes less than or equal to alpha, we can skip the remaining nodes. Pass the values to the alpha and beta. Similarly, pass the initial values for alpha and beta, which will be negative and positive infinity respectively. The lag we had before is now unnoticeable. We can also verify this by comparing the time of the current and previous implementation. Instead of double here, we can make use of integers since they take less memory space. Use -1 as the replacement for the negative infinity and +1 for the positive infinity. There is some issue in our winning logic. Let's consider the given game state. Here, X wins the game when it plays the move in the tile even though it does not satisfy the winning condition. You can pause the video to challenge yourself to fix the bug. We have this bug since we are checking for the match even though there is a mismatch. We should stop matching as soon as it encounters the mismatch. Add two Boolean variables to track the mismatch in both directions. Check if the match has occurred before updating the winning variables. If there is no match, update the mismatch variable to true. Do this for the second case as well. We can break the loop if there is a mismatch in both directions. Reset these two variables and repeat the process of skipping the mismatch for all the remaining directions also. The game is now ready with two modes of play, The first game is the single player game where a player can play with the AI through different levels. The second game is the dual mode where two players can play with each other. I have modified some portions of the code to give the UI of the app a different look. I have also added a gameplay simulation between two AIs. To achieve that, I have reused all the previous code. It randomly chooses any two AIs from the available ones and then the match is played between them. After the game completes, two AIs are again chosen randomly and the game is initiated between them. This process is repeated again and again. Clicking on the board will stop the simulation, which can be resumed by clicking on the board again. Apart from these changes in the UI of the level selection screen, there is additional functionality of choosing option X or O for the players. The map configuration in the level selection screen of the versus mode can be customized using the drop-downs. As you may have already noticed, I have also added the animation when the X or O letter appears on the view. There are also some changes in the settings screen where we can now add the name of the second player. I have also updated the messages in the win game screen, which will vary as per the game result. Furthermore, I have also added different buttons here that may come in handy to the players. You can do much more to this game than I have demonstrated here. For example, make this an online game, introduce a new mode of play with your own rules, etc. I will leave the link to both repositories in the description section below. Alright, we are done with this tutorial. I hope you enjoyed this video. A like is a great way to show your support and do not forget to subscribe for more similar content. Thank you.